Bivariate correlation is a correlation between two variables. Bi mean two and various variables. So in this section, I will explain to you how to do a correlation between two variables and how to find out the relation between these two variables, whether it is a positive relationship or negative relationship, or there is no relationship. The first step in looking at correlation between variables or two variables is to draw a scatter plot. A scatter plot is a diagram that will show the relationship between two variables or more. The first scatter plot is a simple scatter plot that draws the relationship between only two variables. A 3D scatter plot look at the relationship between three different variables simultaneously in a 3D format. If you have three variables or more, overlay scatter plot can be considered as it plots one of the variable in one axis and fix the variable on one axis and then plot that variable against several variables. Or another option is to use the matrix scatter plot, in which the matrix scatter plot displays the relationship and the association between combination of several variables in a format of paired variable. So it's to draw a diagram that has in it paired variable, several paired variable in different combination. Once you've looked at your data, examined your data through a scatter plot and find a relationship and could explore and could reach a conclusion that there is a linear relationship, then it's essential also to look at the data and to examine the data, whether it is parametric data, whether the data are normally distributed and there is no outliers and the variable are continuous. Then parametric test for correlation can be considered. And one of these are the Pearson's correlation coefficient, partial correlation coefficient, part correlation coefficient, Point-Biserial correlation coefficient, or biserial correlation. Again, your data has to fulfill certain assumption to use any of the parametric tests listed here. However, if the data are not normally distributed and the variables deviate from normality, then another option can be used for non-parametric data, and these are Spearman's correlation coefficient and Kendall correlation coefficient.
Scatter plots are diagrams that can be drawn in Spss, and they are used to examine the relationship between variables. And in fact, it is the first step to do in Spss if you are looking at a relationship or association between two or more variables, and if these variables are normally distributed and continuous. And there are four different types of scatter plots. Simple scatter plot, the one to use when you have two variables and you want to look at the relationship between these two variables, whether it's positive or negative or there is no relationship. However, if you have more than two variables to examine, then 3D scatter plot is the one to consider, as it will plot the three variables together in a 3D format. Another option is probably to use is overlay scatter plot, in which the graph examine the relationship between several variables by drawing one variable and fixing it on one axis of the graph and plotting it against several other variables on the y-axis of the graph. The matrix scatter plot also another diagram or chart that can be used to examine the relationship between all combination of multiple variables by looking at pairs of these variables in a combination of pairs of the variable in one diagram. Simple scatter plot is a diagram or a chart that can be drawn in SPSS to examine or find out any relationship between two variables. And what kind of relationship? Is it a positive relationship or is it a negative relationship? By drawing a scatter plot and then also determining whether there is a outliers in your data. And outliers are the extreme high or low data scores in your data. So I will show you how to draw a simple scatter plot in SPSS, how to edit that diagram, and how to export the graph or the chart or the diagram into a Word document or a PowerPoint or a PDF format file, or save it as a PDF file. So here I have a data in SPSS in which I have 8 columns. First one is a dichotomous variable, gender, male and female. And in these data, I'm interested in looking at the relationship between the data 1 and data 3 by drawing a scatter plot to examine the relationship between them prior to doing correlation. The way to draw a scatter plot is to go to click on graphs, scroll down to legacy dialogues, click on scatter plot, then click on symbol scatter, as here we are doing a simple scatter plot. Define, reset this, and I'm going to move data 1 into y-axis and data 3 into x-axis. I could also add a title or a subtitle or a footnote into the diagrams, but here I will leave it blank as I'm going to do this in another way. Up to here, click on the icon for OK. A diagram, a scatter plot diagram is drawn by SPSS, and here we can see the data 1 is on the y-axis, data 2 is data 3 on the x-axis, and the relationship between those two variables is represented by small circles. So if I double click on the graph, another window will come up. Here what I'm interested in, adding a trend line. So if I add a trend line, a line will be added to the scatter plot, and I'm going to remove this small square from here. So if I untick the attach label, this will disappear, and then close this. Now if I want also to remove the gray background here, double click on the gray background. Again here a window will appear, and if I'm going to select the preview, make it white, and then click on apply, the background has disappeared and become white. Now if I want also to remove this small square here, which are 2 for linear, click on it and then right click on it again and click on delete to remove it. Close. Now if I want to do more editing, changing the color of this small circle, just double click on them, and here a window will appear giving you the options to change the size. I can go for 3, and I can go for color, change the color into, let's say, this color, dark blue, and I can also increase the border width, and I apply it and look at it as here. I could also close it and close this and then look at it. It's like a small dot. Now if I double click again, and these are small dots here, no major changes. Okay, also I could change the color of the trend line or the best fit line for a linear options by going at the line color here, and I can change really the style of the line. I can change the width, make it more wider, and check apply, and you see it's thicker. I could change the color into red and check apply. Again, I have here a red trend line and with a blue circles in it. Now what else I can also do, edit if I would like to add a title here or a footnote or a subtitles. The way to do is to right click on this diagram, a list will appear here. I could really add x-axis reference line and so on. So if I would like to add a title, I could click on add title and then type in the title here, correlation. Okay, correlation. And I also could add, should be a little bit capital letter. If I double click on it, I could really change this into capital letter, and again, so I could also add annotation if I would, if you would like to add annotation, and that will be in the graph. You want to remove the annotation, double click on it and then right click again and click on delete. I could also again double click on the diagram and then right click. I will get add text box if I want. I can add a footnote by typing, let's say, figure something, figure whatever, number 1. Now I have a title and a footnote for the diagram. What else? Also I can do some editing for the diagram. If I choose transpose chart, the y-axis and x-axis swap, as we can see here, data 1 in the x and data 3 in the y. And if I don't want to, if I click on transpose again, it will be revert back to the original. So these are some of the common edit you can perform in Spss to shape up your diagram. I could also do some changes here on this. If I click on these x-axis numbers, double click on it, I could change the style by increasing or decreasing the size. I could also change the color if I want. Change the color into, let's say, green. How does it look like with the green, and so on. I could do a few editing here. I could also remove, make it decimal by clicking at the number format and here decimal, change that into 0, so to remove the decimals. I could also change the scale if I would, increasing the scale, minimum and so on. So minimum increment, instead of 5 I can make 2, so I will get more number in between and so on. And the same thing I could do for the y-axis by double clicking on these numbers, and I could go for number format and I stick to decimal 1 and then apply. Again, 1 decimals disappeared, and so on and so on. I can also change the scale, change the label, and change the text and style, and make the color yellow if I would like, or I will stick with this color for a little bit of change. And also I can change the scale here major increment 0.5, I could make it 0.1 to increase it, and if I click on apply and so on, more incrementing added. I could also change the title for the y-axis. If I single click on it, it allows me to change the label on it, whatever, add or remove letters from it. However, if I click on double, I can also change the size here. If I again click on double, I can increase the size of this into 14, apply, and so on. And the same thing going for the x-axis. If I only single click, I can do changes here, correction, data, and so on. And if I double click here, I can change that to 14 and apply, and so on. Now, this is probably the final shape of the diagram. If I want now to export the chart into whether a Word document or PowerPoint, or save it in a PDF format, the way to do that is to go back again to the original graph, right click on it. You have two options here. I'm going to show you the two: copy special or export. We start with export. If I click on export, it's give me an option here, say what type of document you want to export it, as a PDF, as a Word document, as a PowerPoint, plain text, and so on. We will go for Word documents here. If I click on Word documents, and I'm going to save that in one of the folder here, I had correlation, and I will save it here, and I call it correlation graph, correlation graph. Click save, click OK, and click here open the containing folder, and it should automatically open the folder saved here, correlation graph. And if you all click on the correlation graph, you get the graph in Word documents. However, if you saved it in for example, if you go back again and we save it, export that in a PDF format, again call it correlation graph. Okay, again it has also saved it in a PDF format with figure, with title, labels and X and Y axis, and footnotes. And if you want to do it in PowerPoint, it's also similar to that. Now, the other way also to, instead of exporting the graph, is rather than exporting it, is to copy special. In a copy special, if you click on right click again, if I repeat, right click again in the graph, copy special, then click on image. You have to click on image because you want to transfer this diagram as an image. And then if I go here to PowerPoint, and then new page, and then right click, and then click on the diagram, the scatter plot is transferred into PowerPoint. So this is the way to draw a scatter plot in SPSS. Simple scatter plot. In this part 2 section of the video, I will show you how to build a simple scatter plot using chart builder. Back again to the SPSS. Here I have the data, and I'm going to plot a scatter plot looking at the data correlation or relationship between data 1 and data 3, and I'm going also to add another variable, which is the gender dichotomous variable, male or females, and sort out the scatter plot comparison or relationship between data 1 and data 2 and sort them out according to their male or female gender. So to do this, I will click on graph and then scroll to chart builder. Click here OK, and then you will get a window like this. In this window, I'm going to scroll in the gallery down to scatter dot, and in the scatter dot diagram or plot we have here different options, either to draw a simple scatter, grouped scatter, simple 3D scatter, grouped 3D scatter, and so on, and matrix scatter plot. And I'm going to select the simple scatter plot. If I click and drag into this empty box, again here I have the scatter plot ready to place data 1 in the y-axis and data 3 into the x-axis. So now I want to, if I click also on the basic elements, I have another function here. If I want to swap this, I can do transpose to swap the axis, data on the axis. And if I click on a group point ID, this is an extra additional function for drawing a chart. If I am going to add a third grouping, a third variable for grouping these data, so if I group the data using gender here again and click on OK, Spss will generate a scatter plot between data 1 and data 3 and will arrange them according to their gender. These data, male blue and female is green. And if you go back again to the chart builder, I could also, instead of using the grouping, I could go also group the data in rows panel variable and move the gender to the panel. And if you click OK, what happens here is that a scatter plot is generated, splitting it into two diagrams, data 1 compared to data 3 for male and female in one diagram, but split according to the gender. This is when we use the function rows and panel. However, if we select the columns, arrange them by columns, panel variable, and move the gender to the panel, again the scatter plot will be produced, data 1 compared to data 3, but split on columns for male and females according to their gender. So these are some of the editing things that can be done when you use the command for chart builder. And again, if you click also in point ID, and move it to the point and click OK, again the gender of each individual circles, it will be labeled either male or female. And if you go back again, click this one, get out of this one again. If we click, close this one, and then if we click on chart builder, in this chart builder we are going to stick to group by coloring, by gender, color the genders for data 1 and data 2. And if we click on title here in this section, I can really add a title. If we go back again here, we have to move the gender up to here so it can be really finished. So if we click on title, foot, gender, and in this I can type a title for this plot by calling it correlation. Click apply, and then I could also add a footnote and call it figure 1 and apply. Okay, now I think we are ready here to, in the In the options, I don't think we are going to make any changes, nor in the element property. So far, we only click the icon for OK. A diagram will be produced with, again, title correlation, footnote figure 1, x-axis label data 3 and y data 1, and then legend of genders, blue for male and green for female. If I double click on the scatter plot, another window will open. In this scatter plot, I'm going to do a few editing. First of all, I'm going to insert a trend line using linear trend line as here, and I'm going to untick the attach label to the line. So just to get rid of this box, if you click apply, this line is produced. Now if I want to change the background here from gray into white, click on it, click apply. Again, the background is white now. If I want also to get rid of this R square linear, click on it, right click on it, one click, and then left click and then right click and go for delete and delete that things. Close. Now if I want also to either increase these circle things or decrease them, whichever ones, or even change the color for them, I can do that through this window. And I can change even the type, whether square, circle, and choose other shapes. And if I click apply, again the circle's size increased. I also can change the line color. If I would, I could probably put a red color, apply, and a trend line is produced red color. What else I can do editing with this diagram? I could also, as shown before, could change this data y-axis level, increase the font or decrease the font, change its color, put another color. If we can here go for, let's say, light blue, and apply it, this will be light blue, and do the same thing for this one, light blue, and apply, and so on. And also I can change the size and change the style, whatever, bold or not bold or normal, and so on. Furthermore, also I could change also this figure on the x-axis. If I would like to remove the decimal from it and make it 0, so I'm getting just numbers without decimals. I could also change the scale, major increment, make it, let's say, 2, and we get more data, more numbers on the x-axis. Could do the same for the y-axis also. Change the increment 2.2 to increase it more, to give it more, and go for number formats. Here I'm going to change the decimal to 1 to make it 1. I click on OK. Again, as we can see here, this is the diagram in which we have correlation as a title, figure 1 as a note, footnote, then can change the data label on the y-axis, the data 3 or label on the x-axis. So this is the way to do chart builder. Now if I want again to import or to copy and transfer this diagram into Word document or PowerPoint, or save it in a PDF as I shown before, I'm going to close this one. Now I have this plot. I can right click, copy special, and I make sure that I tick on the image, click on OK, and again I could open here a new PowerPoint and paste the diagram here. That's one option. Or I can select the diagram and click on export. Again, I have options here to export it as PDF, as Word document, as PowerPoint. We'll go for PDF, and I'm going to save that in this desktop in the correlation in SPSS, and then I'm going to call it correlation. And if I click save, and then I'm tick the open the containing folder, click on OK. Again, it's exporting it to the folder, and hopefully soon it will show up the location of the scatter plot as shown here in a PDF format. So this is the way to build a scatter plot in SPSS using chart builder with modification, and how to modify it and edit it, and how to export that into different software packages like Microsoft, PowerPoint, Word document, and so on. 3D scatter plot is a diagram used to display the relationship between three variables, continuous variables, and you want to look at the relationship. The 3D scatter is the way to go for. And to do a 3D scatter in SPSS, here I have a data, continuous data from 1 to 7, and I want to look at the relationship between data number 5, 4, and 5, and 6. And I'm going to add additional variables, dichotomous variables for gender, male or female, to sort out the data, males and females, when we look at the relationship between these three variables. So the way to do that in SPSS is to click on Graphs, Legacy, Dialogues, then click on Scatter dot, select 3D scatter, click on Define. I am going here to select data 4 and move it to the y-axis, and I'm going to select data 5 and move it to the x-axis, and I'm going to select data number 6 and add it to the z-axis. And I'm going to set markers by gender. So I'm going to generate a legend showing males and females for the relationship between these three variables. Here I could also add a title for the diagram or graph or chart, and footnotes, and also I can add subtitles, but I will leave it because I'm going to add it in different way. So if I click on OK, a 3D scatter plot is generated, in which you have data number 4 on the y-axis, data 5 on x-axis, and data 6 on the z-axis, and small circles colored green and blue, blue for male, green for female. And again, here I can really do a few modification and editing for the graph. If I double click on the graph, I will get another window, and if I double click on that, and I'm going to change the background into white, so it's becoming white. And I could also change the, again, if I single click on data, I can, sorry, if I single click on data, I can really edit the text within it. And if I double click on it, I can do some modification by increasing the font size, changing the color to red, and so on. And I could do the same thing for 5, changing the color, changing the font, and so on, and click on apply. And I also can do the same thing for the other label in this way. And that's the for the labels. I can also click on the y-axis number, and I can do some modification if I wish. Instead of having 2 decimals, go for 0 decimals. And if I wish also, I could change the scales by changing the increments by 10 to, let's say, 8. So give us more space, or increase that to 15, and so on. Changes back again to 10. And I could do the same thing also for the other, the x-axis, changing the decimal to 0. And again, if I wish, I could also change the scale here, and I could do also the same thing, double click on this number to change the decimal into 0. And I can also scale it if I want, whatever scales I want to do. And basically this most of the things that I really want to do. I also can change the font if I want by clicking red, make it click to highlight it, and so on. So these are some of the modification can be done with this 3D scatter plot. I could also double click on the graph, or single click and then right click. In this right click, I get a list of things that I can do. I can rotate the scatter box whichever direction I want, up and down, right, left, and so on. I can also add title, correlation, and I can add a footnote, figure, figure 1, and so on. What else other changes I can do is hide the legend or show the legend. I can also transpose data, 5 with 6 and 6 with 5, and so on. So these are some of the editing things that can be done on the 3D scatter plot. So now also I can, if I want to export this 3D scatter plot, I can do that by clicking on this, right click on the graph, and then go for export. In the export, I could really export the file in different format, either as a PDF or as a Word document or as a PowerPoint. So I'm going to export it as a PDF, and I'm going to select the folder to put it on correlation, and I'm going to leave it here. I'm going to call it 3D click save, and I'm going to take this, open the containing folder. It is in the software, extract the diagram into the folder, and once it is done, it will automatically go to that folder, and if I double click it is saved as a PDF file. So this is one way to export the diagram. The other one is to right click and then click on copy image, and then you have to make it clear that in this box you need to select the image, format to copy image, and then click OK, and then you can transfer that into Word documents or Excel or even PowerPoint. And if you right click here, choose this, again the diagram is shown in the PowerPoint. 3D scatter plot is a chart or a diagram that can be used to display or to show the relationship between three variables that are continuous. In this second part, I am going to show you how to draw 3D scatter plot using chart builder. Here in this data I have variable data from 1 to 7, and I'm going to draw a 3D scatter plot for data 1 and data 4 and data 7, and I'm going to add to this scatter plot, 3D scatter plot, another variable, dichotomous variable that has gender in it, male or female. And the way to do that in Spss is to click on graphs, select chart builder, and then when this window appears, click on OK. Again, here is a window for a chart builder, and I'm going to click on gallery, scroll to scatter slash dot. In the scatter slash dot I have two options for 3D scatter plot, either a simple one or a grouped 3D scatter, and I'm going to stick with the 3D because it is more inclusive. And I'm going to move the data number 1 into the y-axis, data number 4 into x-axis, data number 7 into y-axis, and I'm going to add gender for coloring, so male will have a color and female have another color. Now if I click on basic elements, I'm not going to make changes. However, if I click on groups or point ID, this is one of the really good feature in the chart builder. Again, here we selected grouping the data based on their gender. So if I click on OK, and I will view the 3D scatter plot, here I get the 3D data 1, data 4, data 7 in different axes, and then these green and blue colors represent male and female. Now this is one feature of scatter plot 3D. I could also untick this and tick row, group them by row panel variables, and I move the gender into the panel here. Again, the diagram is split into two. I have here two 3D scatter plot, one for male and one for female, split according to their gender, and data 1 and data 4 and 7 are drawn here in the 3D scatter plot for males and females. Again, if I go back again to the chart builder and untick the rows, and I group the data based on columns, move it to panel here, Again, it will split the scatter plot into two parts, one for male, one for female, and all the data represented for male in one 3D scatter and females in another 3D scatter. So these are most of the features available to choose from. If I want to go for point ID, again, if we click on OK, it will label the circles either male or females as shown here. Now I will stick to the options of this, group them by gender. So in the y-axis I have data 1, in x-axis data 4, and in the z data 5, and I'm going to untick this one, and I'm going to move data 7. I'm going to move the gender into the set color box. If I click on the title and footnotes also, I can add a title to the graph when it is produced. So if I name that correlation and then click on apply, and I click on footnotes, and then type here figure 1, type apply, and then click OK, a 3D scatter graph scatter plot is produced with a title of correlation and a footnote of figure 1 and the legend of gender, blue for male, green for female, y-axis for data 1, x-axis for data 4, and z-axis for data 7. If I double click on that graph, I will get another window. Here I can really do some editing. So if I want to remove the gray background, double click in the graph again, click on this preview, click on the white things, click on apply. I could also reduce the color of the gray by clicking on this to reduce it to more lighter color. And click on that, click on here, okay, and then close. Again, there are few things we can edit here. If I want to type more in the y-axis label of it, single click, allow me to change it if I want. Double click will allow me to edit the size, the color, and other things that we are not going to look at it. Again, I can do the same with this one, data 4, similar, make it 14 and apply, and data 7 I could really give it also 16 and give it a green color, and so on. I could also click on this number and do some editing. Scale, I could change the scale from 0.5 to 0.4. Again, it's becoming too small. I could also return it back either to 5 or 6. And I could also change the number format. Instead of having decimal to decimal, make it 0, or make it here just 1, because it has fraction in it. And the same thing for the data on the x-axis. If I double click on it and then go for format, number format, make the decimal 0, and then if I would like to add scaling, maybe add another, make the scale smaller, bigger, major increment, or reduce it to 8, and so on. And I could also do the same thing for the Z axis, the data 7. If I click on format and make it 0, and I could go for scale, again I could change the scale, but I will leave it like this. So there are some of the editing options that are available for the 3D scatter plot. Now if I click on the graph, right click on it again, I will get another list which allow me to do more editing. I could really move and rotate the plot. I could also right click on it, add title if I want, add footnote if I want. I could hide the legend, or I could show the legend. I could also transpose the data 4 in place of data 1, or return it back to its original. So these are some of the editing options available for the 3D scatter plot. Now after drawing the scatter plot and finalizing the editing, I will want to export this diagram into into either Word document, PowerPoint, or save it in a PDF file. And the way to do that is select the graph, right click on it, scroll to export, and I'm going to show how to do it in a PDF. I can select PDF, I can select document, I can select PowerPoint. I will stick with PDF, and I'm going to select the folder to put the file in again, and I'm going to call it a 3D scatter. 3D scatter, save, and I'm going to tick this open the containing folder. If I click on OK, the file is exported to the located folder. If I click on this graph again, the 3D scatter is saved as PDF. Now, another way to transfer the figure is to right click on it, copy special, and then tick on this window on the image. So you want to copy it including the image, then click OK, and I could go to open a new PowerPoint, and then I could right click on it and add the picture here, add the diagram or the scatter plot as a picture here in a PowerPoint for presentation. So these are the different ways of drawing a scatter plot and editing it, and then transferring it or exporting it to any other software.
Overlay scatter plot is another type of a scatter plot that can be used in SPSS and can be drawn for data that's or variables, several different variables. So the diagram or the chart, the overlay scatter plot, will display the relationship between multiple variables by holding one variable constant and drawing it on one of the axis, x-axis, and plotting this variable against several variables on y-axis. So the diagram will permit looking at data from several variables simultaneously in one graph by holding one variable constant in one of the axes and plotting it against 2 or 3 or 4 variables. The way to do that in SPSS, here I have data for for 7 variables, and I want to draw a diagram to show the relationship between data number 1 and data number 3 and data number 4 in one diagram. And the best way forward for this is to do a overlay scatter plot. The way to do that is to click on Graphs, Legacy Dialogues, scroll down to Scatter/dot, and from this window select the overlay scatter, then click on Define. A new window will appear, and here we need to sort out our variables, and I need to fix one variable in one axis, and I will move the data number 1 into x-axis and fix it on x-axis and compare it to variable 3 and 4. So if I click on data 1 and then drag it and move it to x variables, and then click on data 3 and move it to y variable, again take the data 1 and place it in x variable, so we hold this variable fixed on x-axis, and then I'm going to select data 4 and move it to y-axis. So here data 1 is in one axis and plotted against data 3 and 4. What I can also do here, I could add the titles and a footnote, but I will do it in a different way. I'll show you shortly. If I click on OK, an Spss will generate an output of the overlay scatter, as I have two variables plotted against data 1, as we can see here, data 3 in blue against data 1 and data 4 in green against data 1. So in the first top set of relationship, as we can see here, it is a decreasing relationship, an inverse relationship, and in the blue circles there is a positive relationship, an increasing relationship between data 1 and data 3. And I'm going to do some more editing on this graph. If I double click on it and double click on the graph to remove the background, click on the white, so to make it white here, and I could change the size of the graph, but I will stick with the same size. Click close, and I could also add a trend line. If I select the file as it is, click on element, fit a trend line. Again, a trend line has been fitted and it is linear, and I will keep the same line color rather than changing it, maybe increasing it a little bit, make it more thicker, and then I'm not going to make any changes here. Click close. Other modification I really could do, if I click on the y-axis, I could reduce decimal number to 0, so to make it look neater really. And I could also click on the x-axis and make the decimal to 0, as it looks here much neater. And I could also get rid of this box, data R2 and R2 for linear, by click on it and then hit the delete button. If I also select the graph and right click on it, I have other options I can do. I can do a title to the graph by calling it correlation. and I could also, it's a small letter, and I could also again select and add a footnote by typing here figure, again it's a small letter, figure 1. If I select the graph again, other options I can do is to hide the legend. I could hide the legend, or I could really show them again. And also there is a function here of which you can transpose the chart. I don't know whether it's helpful, but here if I revert it back again to its original state. So this is some of the editing that can be done to the overlay scatter plot. If I want to export this diagram into other softwares like Word documents, PowerPoint, Excel, or even save it in PDF file, the way to do that is to close this one, then select this diagram, right click, left click, and then right click, and then click on export, and I'm going to save this file as a PDF, or this diagram. Again, as I can see, you can see here they have different options. You can save it as PowerPoint, save it as document, save it as Excel file. So we stick with PDF, and I'm going to place that on a folder here in correlation, and I'm going to call it overlay, and then click save. Again, I'm going to take this here to open the folder containing it. So if I click on OK, it will be exported to the folder, and spontaneously the folder will be open, and it's overlay document. And if I click on it, the diagram is saved in PDF format. Another option is I could do is if I right click on the diagram and then left click and then right click, a small window will appear. Select the copy special and make sure you select the image here in copy special, and then click on OK. The image is saved on the computer clipboard. So if I want to paste it here, click on this image again, the diagram is now transferred or imported into PowerPoint slide. So this is the way to do an overlay scatter plot in SPSS. If you have multiple variables and you want to look at the relationship between these variables by holding one variable constant on one of the graph axis and plotting it against several variables. Matrix scatter plot is a chart or a diagram that permits the examination of a relationship between all combinations of several pairs of variables. So if you have 3 variables or 4 variables or 5 variables, those variables are continuous variables. The data in them or the score in them are continuous, normally distributed. Then it is possible to look at the correlation or the link or the relationship between those several variables each in pairs in a whole scatter plot called matrix scatter plot. And the way to draw a matrix scatter plot in SPSS, here I have a data for several continuous variables and I want to look at the relationship between variable 1 and 2 and 3 and 4 in pairs, and I'm going to add to this relationship another dichotomous variable, which is gender, male or a female. And the way to draw, again, the way to draw a matrix scatter plot is to click on graphs, scroll down to legacy dialogues, then scroll down to scatter dots, and then select the matrix scatter, click on define, and then I'm going to reset this. So I'm going to move to the matrix variables data number 1, as I want to find the relationship between data number 1 and data number 1 and 2 and data number 1 and 2 and 3 and also number 4. And I'm going to set the marker by gender, male or female. I could here add title for the scatter plot or the chart, or I could add also a subtitle or a footnote, but I will show you how to do that once you draw the chart. So if I click here on OK, again, a matrix scatter plot is drawn. And as we can see here on the left hand side, there is a combination. This diagram or this chart shows all the combination and relationship of pairs of variable, such as data 1 and data 2, data 1 and data 3, data 1 and data 4, and again data 2 with 2 and 3 and 4 and so on. So on the y-axis are the data of 1, 2, 3, 4, and on the x-axis, if we call it here, it's data 1, 2, and 3, and 4. And the relationship between pairs of variable is drawn in each one of these squares. And the data also sorted by the gender, male as a blue circle and female as a green circle. So this is the first step when you have a collection of several variables and I want to investigate or examine or look at the relationship or the association between those variables. Then the matrix scatter plot is the one to go for. And I will show you how to do editing on this diagram. If I double click on the graph, another window will pop up. In this window, I am going to do a few editing, like for example, changing the size of the graph into, let's make it 390 instead of 400, so it can fit the window. And I could add to each correlation between two variables that fits in trend line. If I click on fit a line at total, and I will go select the linear one, and as you can see here in the diagram, a line has been drawn to show the data and the relationship between the data. I can also change the color of the line, and if I want the thickness also, instead of going for 1, I'll go for 1.1, 1.5, and I'll click and make the color of it red. And I could also change the end cap. It's not essential. These are some of the editings it could be done for this diagram. Now if we examine this scatter plot, it really we can see simultaneously the correlation or the relationship between data 1 and data 2. Apparently between data 1 and data 2 there is slightly negative relationship, but I can still say it is not not a strong relationship. Even it is weak, even it's less than weak, so I could consider here that data 1 and data 2 there is no relationship. But if we look at data 1 and 3, we can see here that there is a positive relationship, and whenever data 1 increases, data 3 increases. Correlation between data 1 and 4 is a negative relationship, as we can see. Increase in data 1, increase in data 4 will be associated with decrease in data 1. So that is the essence of using the diagrams, matrix scatter plots, to really extract from it and give a hint of the association between variables and the directions of the variables. And if we continue with the editing here, in addition to changing the line here to red, I still can double click on the graph, and I can, if I would change if I double click on the circles, I could also change the circle, but since the diagram is really, the circles are still small, so I will keep it as it is. I am going also to change here, not that major change, I'll keep it as it is, but what I want to do is probably change the background. Instead of making it gray, and I'm going to make the background, if I double click here and click on preview and make it white and then click on apply, I will get a white background, which is much easier to and more neat for presentation. Other editing I can do also, if I single click on the data column and another click on the first one, I can really edit that text by adding or removing thing. If I double click again on it, I could really change the color of it of this text on this side, on the left side, to this color. And I could also do the same for the bottom labels here, data 1, data 2. If I click at any one of them, if I single click, another single click will allow me editing the text. And if I double click, it will open this dialog again, and which I can really change the font of the color, the font, the size, and so on. Different things it's possible to do editing for the diagram. In addition to this, also I can click on or double click on a diagram again, and then either go to options or right click on after double clicking, right click on the diagram, and then I have here a list of editing things that can be used for the graph. So I could add a title here, and I could type in this title correlation, capital letter, and then I could also select the graph again and right click to add a footnote, and then I could type in it, let's say figure number one. Again, I'll click on it. Just a little bit, tweak it around. Figure, oh, come on, where is it? If I expand that,
Okay, do it again, right, double click on it, and then add a footnote. And that footnote I'm going to write figure 1. And also, if again double click on it and double click on the whole graph rather than the thing, than the circles, and I could also do a transpose of the chart, swapping the data on the left and the right. And if I return back to previous, I could also hide or show the ligands here on the right hand side, or show them again. Other things I could do, most of the things, that's all the things that can be done for editing the graph. Now if I want to export the scatter plot into either Word document, Excel sheet, or into PowerPoint, the way to do that is if we close this and go to the original diagram and then select the diagram and then right click on it and scroll down to export. And this export is allow me really to export the figure either as into Excel or PDF or into Word documents or into PowerPoint. So I'm going to use PDF, and I'm going to choose the desktop here, the folder where I'm going to put it, and I'm going to call it here matrix scatterplot, and if I click save, and then if I need to tick the open the containing folder. Once you click on OK, it will be exported into the folder, and automatically the folder will open, and then we will be able to view the figure or the diagram. Here it is saved in this folder. If I click on matrix, PDF file is saved in that format, so I could really copy it and paste it and take it into another into PowerPoint, or put it in Word document. So another way to transfer the diagram is to copy it. If I click on the graph again and then select copy special, and then in the copy special I need to select also the image and then click on OK, it will be saved in the on the clipboard. If I click open a new PowerPoint and then right click on it and then click here on the paste option, diagram is copied and transferred into this PowerPoint slide. Matrix scatter plot. In this part 2 of the video clip, I will show you how to draw this scatter plot using a chart builder. And again, matrix scatter plots is a diagram that can be used to examine the association between a combination of several paired variables. So if you have multiple variables, 3 and more variables, and you want to look at them simultaneously and analyze the relationship between individual paired variable, then the matrix scatter plots is the one to use. And in this part 2, I will show you how to draw it using the chart builder. So here in this data in SPSS, I have variables, and I want to look at variable in data 1 to data 4 simultaneously in a graph, and these data again are continuous data and normally distributed, and then I probably will add to it a 5th variable, dichotomous variable, gender, of individual or participant, male and female. The way to draw the matrix scatter plot using chart builder, click on graphs, scroll to chart builder, a window will appear, just click on it, OK. Another window will appear with empty box. On the left hand side here there is a gallery. We need to scroll down to scatter dots. In the scatter dots window we have several options to choose from. Diagrams for scatter plot, whether it's simple 3D matrix, and this is the one matrix scatter plot we are interested in. So if I click on it, hold it and then drag it into the empty box, and I'm going to add to this plot the data I want to look at. So I'm going to select data 1 to 4 and drag it to this empty box. Again, initial diagram is drawn here. I could do more editing to this graph when I'm in this page. If I go to basics element, I'm not going to make any changes. However, for groups and point ID, I could add a grouping using the gender, male or female. So males will have a color and female will have a color, as we shown here. The circles are now colored coded according to the gender of the individual. If I move to the click on the title and footnotes, I could also add a title to the graph. Here, for example, if I can type correlation, title of the graph, and click on apply, and I could also add a footnote by typing figure 1, and I could click on apply, and I could click on, if I click on OK now, I will get a matrix scatter plot with a title, correlation, footnote figure, legend for male and female, and a diagram that shows all the possible combination between all the 4 variables and the relationship between these variables. If we look at data 1 and data 2, we can see there is no relationship. Data 1 and data 3, there is a positive increasing relationship. Data 1 and 4, negative decreasing relationship. So this diagram shows and allow examining the relationship of multiple variables and multiple combination of variables. If I want to edit here, I could really edit the graph further. If I double click on it, another window will appear. If I double click again on this, I could really do a few changes. Here I selected the marker. Now I need to select the graph itself. So I could really remove the gray background here on the preview and select and apply, so the background will be white. And chart size, I could change the chart size, but according to whichever size, I will just keep it as it is. I could also select the graph again and go to elements and add fit a line into it. Here I had fitted a line to show the relationship. Go again using linear. I could also edit this line by clicking on the lines. I can either change the style, increase the width, and change the color if I want. I will put here a red one, select the red one, so the line will be in red. And if I click on close, again the line are in a red, dark red. I could also click on these circles and I can choose whatever type I would like, shape, and I could change the size, increase or decrease, probably decreasing, that is really too much crowded here. and I just keep it as it is. What else I can also edit? I can also edit this legend or this data or this text on the left hand side. If I just single click on the first one and then another one click, I can really edit that text, add to it or remove from it, whatever, change the description. Again, if I double click again on this legend, I could really change the color of this text, make it green here. If I check apply, it will take for everyone, everything here. I could also change the font size to 14, and so on. These are the things that I really can change on that side of the graph. I could also do the same thing with this one, changing the color, text style, and make it greenish here, and change the size into 40, and then click on apply. So we edited these texts. Other things I also can edit in this graph. If I select the graph and then right click, I have here a list of option things. I could really copy the chart, but I will show later on how to do copying. I could add titles, already add the titles. I could add notation, add a text box, add a footnote, and so on. I could hide the legend, and I could again show the legend. And I select again, see what other options we have here. So those are some of the options that are available for editing the graph. Now, additional thing here I can do in options is to add show charts in diagonal. Again, if I click on add, that's to show the chart in diagonal, and I could also remove it. Again, it shows the distribution histograms for data 1, data 2, data 3, and so on, or I could remove that data. So now if I close this window here and I want to copy this graph, matrix scatter plot, and export that or insert that or place it in a Word document, Excel file, Microsoft PowerPoint, or even save it in a PDF file, the way to do that is you need to click on it, then right click again, and then either have two options, go copy special or export. And I'm going to show you how to do export. You can export the document whatever type you want, to save it in Excel, in a PDF file, in Word documents, in PowerPoint, and I'm going to stick with PDF, and I'm going to save the file in the correlation in Spss. And if I open that, and I'm going to call that matrix M correlation to make a difference from the other file saved here, and then click save. Again, you want to take this one, open the containing folder. Once the export is finished, it automatically goes to the folder and highlight the PDF file, click on it. Again, the figure is saved in a PDF file. I could copy it, transfer it, and so on. Another options is to right click, again click on the graph, right click on it, copy special. In copy special, I will select the image, and in the image I'm going to click copy special and format to copy, including the image, and then I say OK, click on OK, and then I open whatever Word document or PowerPoint or Excel or whatever, and if you click on the paste option here, the diagram will be pasted, copied, and pasted on this PowerPoint. So this is the way to do matrix scatter plots in SPSS using a chart builder. Bivariate correlation, correlation between two variables. Bi mean two and variate mean variables. It is one of the way to measure the relationship between two variables is to determine the strength and the direction of a relationship between two variables on a scale from +1 to -1. +1 indicates that the association is strong and positive and an increasing relationship. -1 indicates a negative relationship, an inverse relationship between the two variables. A 0 value indicates no relationship. There are several different correlation tests that can be used in SPSS, and those tests either can be parametric or non-parametric, and that's depend on the data. If the data are normally distributed and following a certain assumptions to fulfill the criteria for the test, then one of these tests, parametric test, can be used, such as Pearson's correlation coefficient, or partial correlation coefficient, or part semi-partial correlation coefficient, or point-Biserial correlation coefficient, or Biserial correlation coefficient. However, if the data are not normally distributed and it's non-parametric, then a non-parametric correlation test can be used. There are two tests: Spearman's correlation coefficient and Kendall's tau correlation coefficient. One of them can be used to determine the relationship between two variables following certain criteria and assumptions that fulfill which one of these non-parametric tests to use. Bivariate correlation. This is one of the statistical tests that can be performed in SPSS. Bivariate means two variants or two variables. The test looks for a relationship or association between two variables or two groups or two samples. The test that is used is usually Pearson correlation coefficient. The test is used when the data are normally distributed and the variables within the data or the scores within the two groups are normally distributed and are continuous. So it is a parametric test. This test is used to find the relationship between those two variables or two groups, measure the strength, how strong is it, from a scale of -1 to +1, as +1 is the strongest relationship, -1 the strongest relationship, but it's an inverse relationship, 0 as there is no relationship. So the test will measure the strength of the relationship, the direction of the relationship, whether one variable increase the other decrease, or the one variable increase the other increase, or there is no one increase, the other has no association with the first one. So the test will measure the strength, the direction, and the significance of this relationship. So Pearson's correlation coefficient will determine the strength of the relationship on the scale of -1 to 1, the direction of the relationship or the association, and the significance of this relationship. And the way to do that is, here I have a data in SPSS for 4 groups labeled as data 1 to data 4. And on these groups there are scores, and I want to find out the relationship between data number 1 with 2 and data number 1 with 3 and data number 1 with 4. The first step in doing a correlation test, such as Pearson correlation coefficient or a parametric test, is to look at the data through a scatter plot, to look at the data and to find out whether what type of association between them, the relationship, the strength of the relationship, the direction of the relationship. Scatter plot will allow looking at the direction of the relationship and whether there is a relationship or not, and whether there is an outlier or not. The first thing is to do a scatter plot. To do a scatter plot, click on the graph, legacy, display, and then scatter plot. I'm going to use simple scatter. Click on continue, reset this. I'm going to look at the scatter data between data number 1 and data number 2. And if I click on OK, a scatter plot is generated, and as we can see here from this plot, the relationship between data number 1 and data number 2 is not defined. So there is no association between data number 1 and 2. When data number 1 increases, there is a random increase and decrease on the data. So here I can fairly say that there is no relationship between data 1 and data 2. I can confirm that by doing a correlation test using Pearson's correlation coefficient. The way to do that is to click on Analyze and then scroll down to Correlate and then go for Bivariate. Click on Bivariate, reset this. In this Bivariate, I'm going to correlate between data number 1. So I'm going to move data 1 into variables box, and then I'm going to also transfer data 2 into the variable box. Here I'm going to select the Pearson coefficient for correlation or correlation coefficient, and I'm going to ignore the Kendall's 2B and Spearman correlation, as I'm going to describe this in a separate video or separate videos. And since we don't know the relationship between this data, so we always safe to stick to test of significance for two-tailed. However, if I know that data 1 and there is association between data 1, which is increase or decrease, I can choose a one-tailed significant test. But here I'm going to stick safely to as a default for two-tailed significant test. And I'm going to flag the significant correlation. If I click on options, it's not a lot of to choose, but I might select mean and standard deviation. If I want to look at how the mathematical calculation of the Pearson coefficient, I can select the cross product deviation and covariance, but I'm not going to select that. Click on continue, and scale and the style, I'm not going to make any changes. If I click on OK here, what happened here, as we can see, this scatter plot shows that there is no association whatsoever between data 1 and data 2. Pearson correlation coefficient has been calculated using Spss. In the first table, we see here that the data, the mean and the standard deviation for each, and in the second table we see a correlation between data number 1 and data number 2. Again, as we say here, if we compare data 1 to data 1, of course it will be, the correlation will be perfect, and the value for the correlation coefficient will be 1, which is the maximum strength, because you're comparing the data to itself and there is no significant. And as we can see here, the number of the data are 86 scores. Now if we compare data 1 to data 2, we can see here that there is a minus 0.08. That indicates there is a small inverse relationship minor inverse relationship between data 1 and data 2. But again, it is 0.01, so this is really very low, and it's even, there is no significant, we can consider there is no correlation between data 1 and data 2. This is backed up by the p-value, as the p-value here is 0.45, which indicate that it is really not significant. So here we can safely state that data 1 does not correlate with data 2 at all. So there is no significant association between data 1 and data 2. So that's for data 1 and data 2. What about if I want to compare data 1 to data 3? Again, I'm going to repeat the same thing. Draw a scatter plot. Going to move data 1 to y-axis, data 3 to x-axis, or vice versa. If I look at the diagram here, a scatter plot, I can see here that there is a fairly positive relationship between data 1 and data 3, as there is an increase when data 2 increases, data 1 increases. So there is an indication that there is a relationship between those data. To confirm that through a statistical analysis, I will do a Pearson correlation test. So if I click on data, again repeat the same step, keep the same thing as before, click on OK. Here again, correlation table is generated, and now if we compare data 1 to data 3, we find out that there is a correlation coefficient, or we call it here the R. The R, Pearson correlation coefficient, is called R, and the R is 0.55. That is really a moderate relationship, and the sign here is positive, so there is a positive relationship, which means that when data 1 increases, data 3 increases. And this association is extremely significant, as the p-value is less than 0.05. So there is a strong correlation, as we can see here from the scatter plot and from the statistical test using Pearson's correlation coefficient, that there is association, a positive association between data number 1 and data number 2, and this association is statistically significant. Now, if we move again to try to compare data number 1 with data number 4, repeat the same thing again. Scatter plot, remove data number 3 from here, replace it with data number 4, and hit the button for OK. Again, from the scatter plot comparing data 1 with data 4, I can see here the inverse relationship. When data 2 increases, when data 4 increases, data 1 decreases. When data 4 increases, data 1 decreases. So there is an inverse relationship. To confirm this, you need to do a statistical analysis. The way to do that, to go to correlation, bivariate, reset that. I'm going to select compare the data between data number 1 and data number 4. I'm going to keep everything as before. Again, here the correlation says that there is a correlation between data number 1 and data number 2. As we can see here, the value for R is minus 0.722, which indicate that this is an inverse relationship between data 1 and data 4, and since it's minus, and the relationship is really strong, as it is 0.7, and it is significant at the p-value for the statistical test, and the association is really below 0.05. So the graph, scatter plot graph, and the Pearson correlation coefficient R indicate that data 1 and data 4 are associated, and they are in fact negatively associated. There is an inverse relationship between them, and this relationship is really strong. You can call it a strong relationship, and it is significant. So this is the way to do correlation and or association test between two variables. Look at the scatter plot and then backed up that with a statistical test for Pearson correlation when the data are normally distributed and continuous. And Pearson will inform you whether the data are positive or negative. The data correlate to each other positively or negatively, whether the correlation is significant, and the strength of this correlation or length or association. Partial correlation is a parametric test, and partial correlation is used when you have two variable number 1 and variable number 2, and you want to correlate and find the relationship between variable number 1 and variable number 2, at the same time control the influence or the effect of a third variable or a fourth variable or a fifth variable on the effect on one of these variable, all of these variable on variable number 1 and 2, so on both variable. So the test to use is partial correlation, and this test is used when the assumptions are fulfilled. The assumption is that the variables 1 and 2 or variables are continuous, the variables are normally distributed, the variables have no outliers, the variables also has a linear relationship between each other. So the objective of this partial correlation test is to look for and examine the relationship, the strength of the relationship and the direction of the relationship between two variables, whether the relationship is positive or negative on the scale of -1 to +1, and the strength of this relationship and the direction and the significance of this relationship using this partial correlation. And partial correlation in fact uses Pearson correlation coefficient as described in my previous video clips. And the way to do partial correlation, here I have in SPSS a data here in labeled as data number 1, data number 2, and data number 3. And in these data I had already checked that the variables are normally distributed, data 1, 2, and 3, and they are continuous, and they all fulfill the assumption to do correlation and partial correlation. And in this example, I want to compare the relationship between data number 1 and data number 2, and keeping or removing the influence and the effect of the data 3 on relationship between data 1 and data 2. And the way to do that is to click on Analyze and then scroll down to Correlate, and then scroll down to Partial Correlation. And I'm going to reset this. Now in this box in SPSS, I had here to make sure that I move the data into the right box. So I want to compare data 1 with data 2. So these are the two data I want to find. I want to find the relationship between them, and I mean at the same time I want to exclude the effect of data number 3 on the variables number 1 and 2. So the relationship between these two, excluding the effect or the influence of data number 3 on both data 1 and 2. And in this also I want to go for two-tailed test of significance, and I want to display the actual significant level. And if I click on options, I want also to take the zero order of correlation. Zero order of correlation will look at the correlation between all the three variables without partitioning the relationship. So if I click on continue and then click on OK, an SPSS will generate an output for correlation coefficient. Again, if you notice here at the bottom, it says cells contain zero order Pearson correlation. So here in this statistical analysis, Pearson correlation coefficient was measured and calculated for ordered zero order and for partial correlation. So the table is two sections. The top section, which indicate none, which means there is no controlled variable. So all the variables has been correlated with each other without controlling the effect of data 3 on 1 and 2. However, in the bottom section here, data 3, as it's indicated here, has been held constant. So its effect has been removed and the correlation was calculated between data 1 and data 2 without data 3 in consideration. Now, if we go back again here and look at the correlation between data 1 and data 2 and data 1 and data 3 without controlling any variables, we see that there is a relationship between data 1 and data 2. The relationship is positive and it is moderate relationship, as it is 0.551, and the association between those two data are significant as the p-value is less than 0.05. When also look at correlation between data 1 and data 3, we see that there is a correlation, a positive one, but weaker. It is 0.376 compared to 1 and 2, and there is a strong association, significant association between data 1 and data 3. Now, if I remove the influence of data 3 in both, I will look at the correlation between data 1 and data 2. Data 1 and data 2, when controlling data 3, we can see here that the correlation between 1 and 2 is still positive, still statistically significant, but it increased from 0.55 to 0.57. So there is a slight increase in the correlation between data number 1 and data number 2 when the data number 3 is held constant and its influence was removed in both compared data 1 and data 2. So this test is really designed to correlate between two variables, controlling the effect of a third or a fourth or a fifth variable or variables on the original variable number 1 and number 2. Semi-partial correlation, or in another word, part correlation. Semi-partial correlation is different from partial correlation. I have already described partial correlation between two variables in a separate video clip. Here in this video, I will only describe how to do semi-partial correlation or part correlation. This correlation test is a parametric test. The test examines the correlation between two variables when the effect of a third variable is held constant or removed on one of the variables, 1 or 2. So if you have one variable compared to another variable 2, and you have a third variable, then you correlate variable 1 with variable 2 and remove the effect of variable 3 on one of the variable, either variable 1 or variable 2. To do the test, the data has to be normally distributed. The data has to be continuous. The data has has to have a linear relationship. Variable 1 and variable 2 have a linear relationship, and there is no outliers in the data. So the way to do it in SPSS, here I have data, three different variables labeled as data 1, data 5, and data 6. And I want to do a semi-partial correlation between data number 1 and data number 5. And at the same time, I want to hold the effect of data number 6 constant on one of the variable, in this case on variable 6. So the way to do semi-partial correlation is to click on Analyze, and we are going to use regression analysis to perform this parametric test. Here in this box, I am going to move the data into the dependent variable, and I'm going to correlate data with data 1 with data 5, and move also data 6 into the independent. So data 5 and data 6 will be an independent variables. Move them to the independent variables. On the statistics box, I'm going to take on a box that say part and partial correlation. So the software will calculate both the part and partial correlation, and I click on OK. Plot, I'm not going to make any changes, and options, no changes. Here what I'm asking the computer software and the program in Spss is to correlate data 1 with data 5, and at the same time remove the effect of data 6 on only data 5 and not on both 1 and 5. So if I click on OK, the SPSS will generate an output, and in this output, regression outputs, the most important table is the table labeled correlation. Again, and toward the end here we have in the table the correlations coefficient using zero order, partial correlation, and part correlation. For our topic today, this is the important part of the table. In this table, we can see that correlation between data number 1 and data number 5, when we remove the effect of data 6 on data 5, or holding the effect of data 6 on 5 constant, the association between data 1 and data 5 is minus 0.605. So there is a negative relationship, and this negative relationship is moderate, and it is significant as the p-value is less than 0.05. So this table has calculated the correlation coefficient, part correlation coefficient for variable 1 and variable 5, holding variable 6 effect on 5 constant. For correlating variable 1 with variable 6, meanwhile holding the effect of variable 5 on 6 constant, the correlation coefficient was calculated and it is 0.174. This is a weak positive correlation, though it is statistically significant as the p-value is less than 0.05, and it is 0.023 here. So correlating data partial semi-partial correlation between data number 1 and data 6 controlling the effect of 5 on 6, the coefficient value is 0.174. So in this way, I had shown you how to do semi-partial correlation between two variables, variable 1 and variable 5, simultaneously controlling the effect of a third variable on only one of the variable 5, not variable, data 5 and not data 1. Again, the same thing here, semi-partial correlation between two variables, variable number 1 and variable number 6, and holding the effect of variable 5 constant or constant, or removing the effect of variable 5 on 6 but not on variable 1. So this is the way to do semi-partial correlation between two variables simultaneously holding the third variable effect constant on one of the variables. Point-Biserial correlation coefficient is one of the statistical tests that can be used to examine the relationship between two variables. One of these variables is discrete dichotomous, which means it is two categories. Dichotomous mean two categories, like yes or no, live or dead, pregnant or not pregnant. And the other variables is continuous, whether it is a ratio or intervals, but it is continuous and it has to be normally distributed and lacks outliers. So the test will examine the strength of the relationship, the direction of the relationship, and will determine the significance of association between the two variables by producing a p-value. So the point-Biserial correlation coefficient, in fact, is based on using the Pearson correlation coefficient. So it is considered to be a parametric test. And the way to do that in SPSS, here in this data view, I have two set of data, two variables. One is labeled gender, the other one is labeled score. The gender is from 1 to 2. 1 is representing male and 2 representing female, as clearly shown here in the value. And as we can see here, that the gender is a category, so it's nominal, it's either male or female. The score is numerical, so it's a scale from 0 to 100. And in this example, we want to do a statistical test to determine whether there is a relationship between the gender and the score, and find the correlation and the correlation coefficient. For this type of data, since we have here a discrete dichotomous variable which has two categories and a continuous variable, then the way to do that is to use the Point-Biserial correlation coefficient based on Pearson correlation coefficient. To do that is to click on Analyze, scroll down to Correlate, then click on Bivariate. Pi mean 2, variate mean 2 variables. Here in this window, I'm going to look for correlation between gender. So I'm going to move the gender to the variables, and I'm going to move the score to the variables. In the options, and I'm going to also tick the statistics for means and standard deviation. click on continue, and I make sure that the correlation coefficient here we use is the Pearson for this data to test, and I will stick with the two-tailed test of significance to get a p-value. And if I click on OK, here in this output of SPSS we have two tables. The first one is descriptive, showing the mean of the scores and the number of cases. As we can see here, 86 cases. The second table is the correlation coefficient, correlating the data of the gender with the score. Again, as we can see here, there is really a strong statistical association between gender and score, as the value, the R value is 0.87, and this is really a strong relationship, and it is a positive relationship. And the statistical significance, the p-value is less than 0.05. So here we can clearly see that there is a clear association between the gender and the score, and it is statistically significant, and the correlation is positive. To understand better the meaning of this table, I'm going to draw a scatter plot to look at the data, and the diagram of the scatter plot will from it we will determine the correlation between the gender and the score. So if I click on the graph here and I scroll down to legacy and then to the scatter dot, I'm going to select the symbol scatter, and I'm going to click on define. I'm going to put the gender at the x-axis and the score at the y-axis. And if I click on OK, a scatter plot will be generated. As we can see here, it's 1 that represent male, 2 represent females, and the y-axis is the scores. Again, as we can see here, that the scores increases, or the female have a higher scores than male scores. So there is a higher proportion of females score compared to male. I'm going also to double click on this graph. I'm going to add to it trend line, and as we can see here from the trend line, if I just untick the this label and click on apply, and then shrink this, and then shrink this, close this. Again here the output has, SPSS output has drawn a line here to represent that there is a linear relationship between gender and score, and the more the gender moves from male to female, there is an increase in the score, and this relationship is a positive relationship and a significant relationship of, as we determined here, 0.88. So this is the way to do a correlation between two variables. One of these variables are discrete dichotomous and the other one is continuous variable. The way to do that is to do a point-biserial correlation coefficient based on Pearson equation or Pearson method. Biserial correlation coefficient is one of the statistical tests in SPSS that can be used to measure the relationship between two variables, two groups of data, two set of variables. One of the variables is continuous variables, and it is normally distributed variable without an outliers. The other variables is dichotomous, i.e. categorical, but dichotomous with continuity. So it's called continuous dichotomous. An example of that: fail and pass. Failed, anything, any grade, any mark of 60 plus, it is pass. Anything below 60, it is fail, and fail can be fail marginal. So this is a dichotomous variable with underlying continuity. And if we want to compare and find the relationship between those two variables, one of them is continuous, the other one is dichotomous, continuous, dichotomous, or ordinal, the test to use is biserial correlation coefficient. In fact, biserial correlation coefficient works by determining first the point-biserial correlation coefficient, which I've already described in a previous video clip. Once the value, the R value for the point-biserial correlation coefficient is determined, a formula given below can be used to work out and calculate the biserial correlation coefficient. And the equation states that the coefficient for biserial equal to the coefficient of point-biserial multiplied by the square root of P1 and P2. P1 is the proportion of cases in category 1, or the percentage. P2 is the proportion of cases in category 2 divided by an ordinate y. Y is an ordinate of the normal distribution, and this value can be extracted from a table of the standard normal distribution table following a standard normal distribution curve. So to do this test in SPSS, I have here a data sorted out in two columns, two variables. One of them success, pass and failure, as you can see here, pass and failure. And this success or failure is a dichotomous, as I have labeled failed 1, 2, pass. And it is an ordinal, as success is just categories, and the score is numerical. So the success, pass and fail with marginal failure and or the ordinal dichotomous. This is a dichotomous or ordinal dichotomous variable, and the score is a continuous variable from 0 up to 100, and I've checked that it is normally distributed without an outliers. To find out if there is a correlation or relationship between this dichotomous variable, continuous dichotomous variable, with this continuous variable, first of all we have to calculate the point-biserial coefficient, and point-biserial coefficient can be calculated using Pearson correlation coefficient. I've already described that also in a separate video for how to do Pearson's correlation coefficient. The way to do the analysis and test is to click on Analyze, scroll to Correlate, Bivariate, as pi stands for 2, variates mean 2 variables. If I click on bivariate correlation, I have here a box. I'm going to correlate between the success, which is the dichotomous variable, with the score, which is the continuous variable. And I'm going to keep the tick for correlation coefficient for Pearson correlation coefficient to calculate the coefficient for the point-biserial. And I'm going to stick with the two-tailed test of significance as shown here. And if I click the OK icon, I get this table. This table shows that there is a correlation between success and score, and the value for the correlation is 5.504. So this is really a moderate
relationship between those two variables, the dichotomous one and the continuous one, dichotomous and the continuous variable. And in fact, there is a strong, significant, and this is really, this relationship has a significant value of less than 0.05. So this is really credible and statistically significant relationship between success and score. The value for this in this table can be considered as here point-Biserial correlation. And then now we need to calculate the biserial correlation RB, and to calculate the RB we are going to use the formula here given below. As we can see here, the RB is already determined to be 0.504. Now I need to determine the P1 and the P2. To determine the P1 and the P2, the way is to click on Analyze, Descriptive, Frequencies, Reset, and then I'm going to find the proportion or the percentage of pass and failure. So I'm looking at the dichotomous variable, and I'm not going to make any changes here, just stick to this and click on OK. In this table here, success and failure, it's a fail and pass. So there are 58.1% fail and 41.9% pass. So the proportion here is 0.581 for fail, 0.419 for pass. So I'm going to use this value to and apply them into the standard normal curve table here. As you can see, large portion, small portion. So our first p-value from this table here we've shown is 0.581, and the other one is 0.419. So we need to use these two values on this table here. If we look at the larger portion here of 0.58, if we scroll down from 0.581 up to here, I have labeled this value with a red square or rectangle, and this is the value 0.581 closest to 0.581, and then for the smaller portion 0.419, the closest one is here. So from this coordinate we can calculate the y, and the y here is 0.3902. This is the way to work out the y ordinate from that standard table using a larger portion and a smaller portion, P1 and P2. Now I need here to use a calculator. So if I click on calculator here and back again to statistics and the calculator, so what I'm going to use the formula. First of all, I'm going to put the value for calculate first the portion 1 and portion 2 multiplied, then square root of it. So the P1 is, as we can see here, is 0.581 multiplied by 0.419. If I hit equal, it will be 0.243 and so on. If I do a square root for this value, now I've got the square root of proportion 1, proportion 2. Then I need to multiply that by the coefficient of point-Biserial following the equation. The point-Biserial is determined here is point, so multiplied by 0.504. Hit the bottom equal, so I still get 0.248, and I need now to divide that by the y ordinate, and the y ordinate is, as I've already calculated, that is 0.3902. and if I click OK, then this is the value for points for the Pearson Biserial correlation coefficient 637. This value, as we can see here, the biserial correlation coefficient is 0.637. The point-biserial coefficient is 0.504. So this is higher. The value for this is higher than the point-biserial. So this is the way to do and measure and calculate a relationship or a link or association between two variables. One of them is continuous variable, normally distributed. The other variable is dichotomous variable when there is an ordinal in it, i.e. there is continuity of it. The way to do it is to do a biserial correlation coefficient following the formula given, using two tests, the Pearson correlation coefficient and the point-biserial correlation coefficient, to work from them to extract the point-biserial and then use the equation to determine the value for the coefficient for the biserial.
Bivariate correlation. Spearman's correlation coefficient is a non-parametric test, is one of the tests available to look for and examine relationship between two variables or two groups or two samples. When the scores within one of the variable or one of the group is not normally distributed, then you cannot use a parametric test like Pearson's correlation coefficient. Spearman's is the one to use when you have one of your data are not normally distributed. In fact, one of the conditions for Spearman's correlation coefficient is that one of the data need to be ordinal. Ordinal means non-parametric, means that the data are in order like A, B, C, D, E, F. So this is called ordinal. The second variable can be continuous or can be again ordinal. So Spearman's correlation coefficient is a test for finding out the relationship, association, link, correlation between two set of data and two variables or two variables. The test well measures the strength of the association by assigning a factor or a value called RHO coefficient. If the value is -1, then that means the strength, that's the strongest correlation, and minus indicate inverse relationship. One variable increase, the other decrease. And if the raw coefficient is +1, then it is a positive relationship. One variable increase, the other increase. If the RHO or the coefficient close to 0 or 0, then it means that there is no correlation between two variables and there are no link. So the test really measures the strength of the correlation, the direction of the correlation, increase or decrease, and the statistical significance of this correlation. The way to do that is in SPSS is to look at this example. I have here 4 columns or 4 variables from grades, study hours, variable 1 and variable 2, I call them. So I need to find whether there is a correlation or a relationship or a link between grades that the student obtain from and correlate that to the study of hours, and then a variable 1 and a variable 2. Again, grades means 1, 2, 3, 4 indicate A, B, C, D, E, F. Give them a labeling. So the variable in the grades are ordinal. It is not normally distributed. It's not a continuous. The study hours also is a continuous, because it can be 1 hour, 2 hour, 3 hour, 4 hour, 5 hour, 6 hour, 12 hours, 13 hours, and so on, 15 hours of study. Variable 1 also is a continuous, and variable 2 is a continuous. I've already checked the distribution of these data. Again, here I want to correlate the association between those variables and to find out whether there is link between them and what kind of relationship. Is it increasing, decreasing, and is it significant or not significant? For this test, for this data, we are going to use a test that is non-parametric. It's a Spearman's correlation coefficient. If I click on Analyze, then Correlate, Bivariate, go for Bivariate Correlation, and I'm going to move the grades to the variables section, the study hours to the variable section, and then variable 1, and then variable 2. Here in the coefficient correlation, I am going to untick the Pearsons, because I'm not going to use the Pearson, because here our data are not normally distributed. One of the variable or the group are ordinal, so we cannot use Pearson. We only can use Spearman. And Kendall also probably can be used, but not in these circumstances. I will have another video describing when to use the Kendall to association or correlation test. Regarding the test of significance, since we do not know the relationship between studying and the grades, whether it is positive or negative, so we will stick with the default test of significance, two-tailed significance. However, if I know the relationship, whether it's positive or negative, then I can take one-tailed. But in this case, in our current case, we use the two-tailed. I'm going to keep the flag significant correlation ticked on. If I click on OK, a table will be generated as we see here and labeled as correlation. What does the correlation do here? Here, what's in fact done is that the Spearman's test took the data from column number 1 and column number 2, and column number 3, and column number 4, and put them in ranks, sort them out in ranks, and then used the Pearson correlation coefficient to find out the correlation or the association. So in this finding out here, it is calculated, the Spearman row calculated, looking at the grade, the relationship between the grade and study hours, variable 1 and variable 2. Again, if we correlate grades with grades, we'll get a perfect relationship 1, which is the maximum, which is perfect. However, without giving statistical, because you are correlating the variable to itself. When we correlate the grades with the study hours, we can see here that we have a value of 0.45 and a positive value, which means that there is a positive relationship between number of study hours and the grade achieved. So if there is increase in the number of study hours, there is an increase in the grade, overall grade achieved. So there is a positive increasing relationship between these two variables. And the statistical significance is really less than 0.05. So there is a statistically significant correlation between the grades and the syllabus and study hours, and this is very significant at the two-tailed significance as indicated here. So the grade is associated with the study hours and linked to the study hours, and it is significant and it is positive. However, when we compare and correlate the grades with variable 1, we get here a positive correlation, which is a weak positive correlation, 0.156. So there is a correlation between grades and the variable 1. However, this correlation or this association is not statistically significant, as the p-value is 0.12. So in this case, I can safely say that there is a weak correlation between grade and variable 1, but it is not significant. So we cannot really rule out the relationship between grades and variable. Again, the same story if we look at and correlate between grades and variable 2. We get here a raw value of minus 0.046, which is very, very close to 0. However, it is minus, so there is an inverse relationship and a minus, a minus, so it's really slim correlation between grades and variable 2. However, the statistical significance and the p-value has shown that it is 0.65, so it is not statistically significant, as the two-tailed significant value was 0.65 and it is greater than 0.05. So thus here we can safely state that the correlation between there is no correlation between grade and variable 2, as there is the statistical significance, there is no statistical significance between this correlation, and the value for the raw is very low and close to 0. So again, here we can see from this example the correlation between variables, two variables, can be either positive or negative, statistically significant and not statistically significant. So the raw can tell you really the direction of the relationship, the strength of the relationship, and the significance of the relationship. Again, here also, if we look here, the other side, it's cross correlation between these variables. And if we look at Spearman's correlation with study hours with variable 1 and 2, again there is a weak correlation, 0.05 close to 0, and with variable 2 close to 0, statistically significant 0.6, 0.8, so there is no statistical significance comparing these two. If we compare variable 1, again it's with variable 2, we can see it's 0.01 and it's 0.9, so there is no statistical significance between those variable 1 and variable 2. So this is the way to look at correlation between two data, two variables, two groups that have scores in them or data on them that one of these groups are not normally distributed, i.e. ordinal, and the other variable either ordinal or continuous, is through using the Spearman's correlation coefficient. Kendall's tau correlation test is a statistical test that can be used to find out a correlation or association or a link between two sets of data, two groups of data, or two variables. And those variables can be either ordinal, in which the data are in order like A, B, C, D, E, F, or ordinal with continuous. One of the variables is ordinal, the other is continuous, but it is not normally distributed, i.e. there is an outlier in the data, whether an extreme value or a low value. So the test is done or carried out or used when the data are not normally distributed. So it is a non-parametric test. The test also can be used when you do have a small data. You have two groups that have small values in it. The numbers are really small. So then Kendall's tau, the one to use. How to do the test? We'll show you in Spss. Here I have 4 variables. The first one is labeled ordinal, as it goes from 1 to 6, indicating A, B, C, D, E, F. So A for 1, B for 2, C for 3, and so on. And then there is variable 1, variable 2, and variable 3. Variable 1 is again a ordinal data, as it is 1, 2, 3, and variable 2, 3 is also a continuous variable. So again, as we can see here, we have a small number of data, 30 cases, and we need to find if there is a relationship between these 4 different variables. And the test to go for is Kendall tau correlation test, as we have here small number of data, small samples, two variables are either ordinal or continuous, that are not normally distributed. And to do the test, click on Analyze, scroll down to Correlate, click on Bivariate, which means bivariables, 2 variables, and I'm going to compare the ordinal with all the 4, ordinal with all the 3 other variables. If I move them into the box under variables, and I'm going to use here the Kendall's tau correlation test, and I'm going to untick Pearson and tick the Kendall's tau test. For the test of significance, I'm going to keep it as two-tailed, a default test, two-tailed statistical test. I only can use one-tailed if I really know the direction of the relationship, whether there is an increase or decrease. Then we can use one-tailed test of significance. And then I'm going to tick flag significant correlation. So this test will measure the strength of the correlation between 2 variables, whether it's strong or weak, positive or negative. As it will give a value from -1 to +1. -1 indicate very strong negative relationship. One variable increase, the other decrease. +1 is a positive relationship, which is a strong one. One variable increase, the other increase. When it's the value for the correlation is 0, then there is no correlation. So that test will calculate and determine the strength of the correlation, the direction of the correlation, and the statistical significance of this correlation. I'm not going to change anything in the options. Key is the same and style the same. So I'm going to click on OK. A table of correlation will be generated. Again, the software will correlate the first variable, which is called ordinal, with itself, and then with variable 1, with variable 2, with variable 3. So in this case, as we can see, correlating the variable to itself give a 1 coefficient, correlation coefficient of 1, as itself correlate with itself. If we correlate the ordinal variable with variable number 1, we can see here that the coefficient is 0.425. So there is a positive correlation, and this correlation is moderate correlation, and it is statistically significant, as the p-value is 0.004. So here we can safely and with confidence state that the correlating ordinal with variable 1, the relationship is positive, and the coefficient is 0.42, and it is statistically significant. And when there is an increase in the ordinal, there is increase in the variable 1. So it is a positive correlation that's statistically significant. However, if we compare the ordinal to variable number 2, again we get a positive coefficient, which indicate that the relationship is positive. So the increase of the ordinal, increase of the variable, both of them increase together, but the coefficient is very low as it is 0.1, which indicate there is a very weak correlation. However, the p-value is not significant, so the statistical show that the association is not significant as the p-value was 0.4, and our cut-off point for p-value is 0.05. Anything lower than 0.05 statistically significant. Here it's 0.4, so the correlation, there is a weak correlation, but it is not statistically significant. So we can state here that there is a weak correlation between ordinal and variable 2, but the correlation, and it's positive, but it is not statistically significant. When we also correlate the ordinal with variable number 3, we get a coefficient of minus 0.28. This indicates that this relationship is negative, inverse. Ordinal value increase, then the variable score within the variable decrease. So it is a minus relationship, and it is weak relationship. However, if we look at the p-value, find it is really statistically significant, 0.037. So this indicates that the ordinal variable correlate with variable 3 negatively, and either the association or the relationship is statistically significant at a cutoff point of 0.05, because 0.03 is smaller than 0.05. So fairly here we can see that, state that the correlating ordinal with variable 3 is, there is a correlation, that's a negative correlation, and it is statistically significant. Again, if we look also at the column here, we can look at correlation between variable 1 and variable 2. The correlation is 0.08, weak correlation, but not statistically significant. If we correlate variable 1 with variable 3, again the correlation coefficient is very weak, 0.05, close to 0. And the p-value is very, very, very high, so this is not statistically significant correlation between both. Again, if we correlate variable 2 with variable 3, we can see here that the correlation is very weak, positive but very weak, and it's not statistically significant, as it is nearly 0.9, close to 1. And if we correlate variable 1 with variable 3, we can see there is a weak correlation that's positive, close to 0, and it's not statistically significant, and the value is 0.68. So from this it is very straightforward to make a conclusion when comparing two variables that are not normally distributed, when the data are not parametric and these data are small, the data on the groups are small, we can compare two variables using the Kendall's correlation coefficient.